I have some printed copy for you out here. So today is our buffer lecture for midterm 2. So the structure is basically first we'll go over a summary of the topics, and for each topic I'll briefly say, hey, what this lecture is about, just to refresh your memory on what we discussed in these lectures. And then I'm gonna try again to see like how do you use the thermodynamic, how are the thermodynamic relations derived? What does it mean when we say derivation of these thermodynamic relations? How do we get to the Maxwell relations, dependence of state functions, and how to use the dependence of state functions to calculate changes in these state functions, or like, aka, how do we actually use these thermodynamic relations that we derived in class? All right, so these will be the second topic. We'll do one derivation problem together, and then we'll do a true and false problem to elucidate the conceptual ambiguity regarding chemical potential. And at the end, we'll do one more example if we have time on calculation of changes in state functions. So that's the structure of today. All right, getting started. So far, we have several topics. We have several lectures we covered all the way after midterm 1, which we start by looking at the physical meaning of entropy. So in lecture 11, when we're talking about the physical meaning of entropy, the one take-home message I want you to remember is we use the mixing of ideal gases to try to demonstrate what exactly is entropy. At the end of our lecture 11, we end up saying, okay, so entropy must be related to some kind of constant times the natural log of probability. So this P here is probability plus a constant C, right? Or more typically, we are talking about calculation of delta S, right? So the change of entropy in one state versus another. So you're taking the initial probability, the final probability over the initial probability. So we're talking about S2 minus S1. So this C will cancel out. We get K ln P2 minus K ln P1. Since we're looking at the natural log, you write it in, that's K ln P2 over P1. Right, so that probability you can either calculate using your knowledge on probability, and at the same time we can also calculate delta S from thermodynamic point of view. Remember, we built the reversible path in previous lectures. So in lecture 11, the key take-home message is that what is entropy? So entropy is a form, or entropy describes the probability of occurring of a thermodynamic state. All right, so that's lecture 11. Then lecture 12, 13, 14, and 15, these 4 lectures are internally connected to each other. So in our lecture 12, we started by introducing material equilibrium. Like, what is material equilibrium? It contains phase equilibrium and reaction equilibrium. Right, and then we define, since we care about what is minimized at equilibrium, based on entropy is maximized at material equilibrium, we end up defining our 2 new thermodynamic state functions, a Helmholtz energy, which is A. Remember, A is by definition U minus Ts, and G is by definition H minus Ts. In lecture 12, we also went over the physical meaning of Helmholtz energy and Gibbs free energy, right? So Helmholtz free energy is minimized when when we have isolated system, constant temperature and constant volume, and my Gibbs free energy is minimized at material equilibrium when we have constant temperature, constant pressure. All right, so in this part, it's more like conceptual understanding. And I just want to remind you on the 3 figures that we went over in class. So when we look at, for example, entropy versus time of an isolated system, have the entropy is always going up, and we have ds equals to 0, or entropy maximized at equilibrium. Right, and prior to equilibrium, you have ds larger than 0 prior to equilibrium. And for Gibbs free energy and Helmholtz energy, it's the same idea. But now what we have, let's say we have our plot like this. And we tell you this is the plot, that this is where equilibrium is. This is isolated system, constant temperature and pressure. So what is this term here? Constant temperature and pressure. This property is minimized at material equilibrium. What's that property? G, right? And likewise, we could also ask you to say like, hey, this is A, and we have isolated system, constant TV, and we can ask you to plot how does my Helmholtz energy change with respect to time at constant temperature and volume. And that's basically the same curve, and you can identify, hey, this one is our equilibrium. Yes?
For A, it's also material equilibrium?
Right, so for both G and A, we're talking about material equilibrium. Now I want to raise one question. So as chemists, we deal with Gibbs free energy very often, but we very rarely talk about the Helmholtz energy, right? So can you think about why that is the case? Why as chemists, we care about Gibbs free energy more, or we use Gibbs free energy more? Right, so if you think about it, we chemists, we can easily set up reactions that is at constant temperature by putting it in a water bath. We can easily control the pressure to be constant by saying that's just 1 atmosphere, our normal atmospheric pressure. So it's easier for us to keep a reaction at constant temperature and pressure. While the Helmholtz energy, this one is more used for chemical engineer, like you have a chamber of fixed volume, and then you keep the temperature the same, so it's easier to use Helmholtz energy. So just a fun fact, like that's why chemists use Gibbs energy more. All right, so that's lecture 12, right? So knowing how A and G are defined, what exactly does A and G tell us, right? So what's the physical meaning of A and G? So A tells you the total amount, the maximum amount of work done by the system. And for G, that's the maximum amount of non-PV work done by the system. So those are the physical meaning of A and G. Then for lectures 13, 14, and 15, these parts are naturally related. Now we have 4 fundamental state functions in thermodynamics that we care about. We have internal energy U, we have enthalpy H that we defined before, and now we have Gibbs energy and Helmholtz energy. So the entire chapter 13 and 14 is telling us the relationship between these thermodynamic state functions and also between their partial differential equations. Later on, we end up saying like how to present my state function or the changing state function in thermodynamic measurables. And I'll go over these 3 sections in more detail later on. So after 13, 14, and 15, we then moved on away from equilibrium to focusing on positions that's prior to equilibrium. Right, so in that case, we introduce the idea of chemical potential. Right, so when we say chemical potential, what are we saying? What we're having here is, say, my mu, I, alpha. So knowing what each term means, I'm just going to finish writing it, and then we'll talk about it one by one. And I alpha, PP, N alpha, J not equal to I. Right, so what does each term mean in this definition for our chemical potential? So this alpha here tells us that's the phase. I here tells you which chemical species we have in mind, right? So in a example, for example, we can have like say A plus B goes to C. So how many different chemical species are there in my system? We have I can equal to A or B or C, right? So we have a total of 3 of them. Now think about what is my chemical potential. Now the alpha denotes 4 different phases. Imagine we only have 1 phases. How can we simplify my definition of the chemical potential? Let me make some space. So what do we have? If we only have like say 1 phase, then we can simplify that equation into just saying like dG over dNi at constant T, P, Ni not equal, Nj not equal to I. Right, so here we're simplifying that general definition for chemical potential into a 1-phase system. So one of the key points that people may miss is this point. So when we're looking at this delta G, this is a change of free energy of my entire system. Right? So if you consider my system containing A, B, and C, we can write the chemical potential for A, B, and C. What does that look like? So we'll have mu A equals to the total differential, the differential of my total Gibbs free energy over the NA, T, P, and B, and C. Right, my mu B will likely equals to the total, the differential of the total Gibbs free energy over the NB, TP, NA, and NC. So the most important thing here is do not write that dG as the dG of the species. If you write like dG for my species A, that's telling me that's a Gibbs free energy of my pure substance A. That is going to be different for the total free energy of my entire system containing A, B, and C. With me so far? So what's the difference here? So the total Gibbs free energy, or the total Gibbs free energy equals to GA plus GB plus GC. But when we're defining the chemical potential, the most easy to miss point here is this one is the total Gibbs free energy. And when we're talking about the chemical potential of a specific species, I, we're taking the differential of the total Gibbs free energy over the change of that one species only, while keeping everything constant. All right, and in the chemical potential part, we also went over several things, like what do we know about chemical potential? For example, we know that the sum of my chemical potential, mu I dNi equals to 0 at equilibrium. Where does this come from? Now, if you think about it, coming from our definition, we know that this term basically gives us my dG, or I should say constant, isolated, constant Tp. So what we know is that my dG equals to 0 at isolated system, constant Tp. And my dG equals to that sum of the mu I dNi equals to dG. Right, so it's this summation that equals to 0 at material equilibrium. So what if I ask you the question, is this statement true at this condition? So that's not true. That's not necessarily true, right? So what we find out is at material equilibrium, we know that dG equals to 0. We know that the change of the number of species, basically that summation goes to 0. But it doesn't tell us my internal, my chemical potential is 0. All right, with me so far? So we have our chemical potential defined, and we have this term here. Let me just erase the wrong one so you don't write it. So that term equals to 0 at material equilibrium, constant Tp. And we'll do some true and false problems on the chemical potential later on. This is just to try to get a little bit of the muddiest point to resolve. And later on, we discussed reaction equilibrium. So this one is more straightforward, right? So we have a general reaction. It's the summation of the stoichiometric coefficient times AI. So now in this summation, what does that mean? So in this case, if we have a reaction like AA plus BB goes to CC, we ask you what is the stoichiometric coefficient of my chemical species A? And that's negative A for my stoichiometric coefficient A, right? So know how to write it. And later on, we also talk about the heat of the reaction. So the delta H of the reaction at certain temperature equals to the sum of my stoichiometric coefficient times the molar enthalpy of each species. And using the Hess law, along with the heat of formation, we have a way to use the thermodynamic table to calculate the heat of the reaction. And in this lecture, we also defined the standard state. So remember, standard state is P naught equals to 1 bar. And then the temperature is defined, but it doesn't need to be any specific temperature. You can have a standard state at 273 K. You can have a standard state at 298 K. And then the lecture 18, we discuss how scientists actually design experiments to measure the heat of formation. And then in our last lecture, we went over conventional entropy. So in this part, the first section of our class is to use the third law of thermodynamics to find out that at 0 K, my entropy, we are arbitrarily setting that the absolute entropy equals to 0 at 0 K. And then we went over a series of calculations to show like how to do a, like say isobaric temperature increase, right? So that delta S equals to Cp over T dt. And by solving that integral, we can get how the entropy change. Now in here, we specifically mentioned that things might be a little bit different when we're talking about 0 to 15K, since we don't have a way to measure what Cp is. And we can estimate this integral to be the Cp m low over 3. Right. So this is just something we just discussed in our last lecture. If you forgot, like just review a little bit in our lecture notes. We also went over our phase change at constant Tp, and that delta S equals to delta H phase transfer over T phase transfer. All right, so those are the things we went over in our last lecture. And that's it. That's the coverage of all of our midterm 2. And that's a quick summary on what we discussed so far. And let's go, bless you. And let's dive into some of the example questions I promised you. First of all, again, a quick review on the thermodynamic relations. So in this, yes? I uploaded the annotated version, so you'll have it. So for this table, basically I want you to look at it and think about it. How did we use the top basic equations and the calculus toolbox to get everything in the bottom bracket? All right, so how do we do that? Just thinking about that process. Like for example, if we randomly just pick, let's say I want to start from du equals to TdS minus PdV, and the definition of my Helmholtz energy. How do I get this dA equals to negative S minus PdV? right? So think about it. Do you know how to do that derivation? And the way is very simple. Is we start by writing my A equals to U minus TS. And in my calculus toolbox, what do we have? We can, first of all, we can take the differential on both ends to get dA equals to du minus dTs. Right, and in my calculus toolbox, this is what we have, the dxy equals x dy plus y dx. And thus my dA equals to du minus TDS minus SDT. And in here, I know my du equals to TDS minus PdV, and then minus TDS minus SDT, right? So these two cancel out. We get our dA equals to minus PdV minus SDT. Right, that's how we get to our set of Gibbs equations. And what about here? What about how to get it from my Gibbs equation to these expressions? Yes. Right, so this is the one we were using. So in this case, what we're writing is we know A is a function of T and V, right? So we can write out the total differential of A. So if we write that out, we have dA equals to dA over dt at constant V dt plus dA over dt at constant V, dV at constant T. Right, and in here, what do we have? We know that this term is in front of dV. That must equal to negative P. Right, and likewise, this term in front of dt must equal to negative S. Right, and the third toolbox we used in our calculus toolbox is the Euler's reciprocity relations. Right, so in this case, we have a similar kind of version. So we have M equals to minus S, N equals to minus P, X equals to T, Y equals to V. So we're just rewriting this dm over dy at constant X and dN over dx at constant Y, etc. With all these things in my second toolbox, we then are ready to express my thermodynamic state functions into measurables, right? So there are things we cannot measure, like how does entropy change with respect to pressure at constant temperature. These are the things we cannot measure. So using thermodynamic relations, we can express the dependence of my state function into different measurables. So for example, we can have du over dV at constant T equals to T alpha over chi minus P. And how did we do that? We start from U equals to du equals to TDS minus PdV. Right, you divide both ends by dV, you get du over dV equals to TDS over dV minus P dV over dV. And that cancels out. So looking at the constant temperature process, or since it's a state function, we can define a temperature constant process. We have my du over dV at constant T equals to T ds over dV at constant T minus P. And later on, using my thermodynamic relations, we find out this term equals to dP over dt at constant V, which then equals to alpha over chi. All right, so this part also includes the volume and temperature dependence of internal energy, pressure and temperature dependence of enthalpy, pressure and temperature dependence of entropy, etc., etc. I'm not saying like you need to derive everything whenever you see that question on the exam, but it's important to know where this equation comes from. And now we have all these equation sheets. How are we actually gonna use it, right? So that's our next question here. So this is the example question we'll do together. Let's see how much time I have. Let's see how far we go. So if you don't have a copy, I have printed out version in the front, so you can come and grab a copy, and then we'll do these together on the board. All right, so for this question, if we read it together, it basically says, a certain gas obeys the equation of state. So what is equation of state? Equation of state gives us relationship between pressure, volume, and temperature, right? Can you prove that for this gas, what is your partial differential of U over V at constant T? That's our internal pressure, or we call it volume dependence of internal energy, right? What is the difference between your CPM minus CVM? And how can you prove that mu J(T) must equal to 0 for this gas? We have our equation of state to use. Do you want me to leave it at here or leave it at the equation of state? I mean the equation sheet. Okay, I'll leave it here then. Okay, I'll leave it here, and if you want me to go back to equation sheet, we can do that. So first question, what is our du over dv at constant T? That's the volume dependence of internal energy, right? So in our previous lectures, we went over the derivation. So here we can just use du over dv at constant T. That equals to, what do we have? The one we just did here, T alpha over chi minus P. And this alpha over chi term is effectively the dP over dt at constant V. So what does this question is asking? This question is basically asking you, now we have these partial differential equations. Can you use our equation of state and solve this partial differential equation, solve this derivation, right? So what do we have here? We want to use our equation of state, which is PV equals to nRT times 1 plus BP. Note that this Vm equals to V over N. So that's the same equation of state we had before. So now we're just trying to solve how does my pressure change with respect to temperature in this equation of state. There are multiple ways you can solve it, but in here, since we have pressure on both ends, it's not super straightforward to see how to solve my equation of state just directly by dP over dt. So alternatively, we can use my dP over dt at constant V, dP over dV at constant P, and dV over dP at constant T. This goes to -1. Right, so that's just our calculus. But since I have all the information, let me come back here so you can see the toolbox we're using. Now, if we focus on the first one, how does temperature change with respect to volume? So first, I can rewrite my equation of state as temperature equals to PV divided by NR, 1 plus dP. So my dt over dV at constant P. So here, the only thing we're taking differential is this volume here. That equals to P over NR times 1 plus dP. And then we have our dV over dP at constant T. We write volume equals to nRT, 1 plus dP divided by P. So my dV over dP at constant T. This one. So dV over dP at constant T. On the top, so my nRT, 1 plus BP, this doesn't have any pressure in there. So that goes to the negative nRT. This BP term, the pressure and pressure will cancel out. So we only have the first term. Or if we write that out, that's nRT over P plus P nRT. So this term doesn't have any pressure dependence. So it ends up having negative nRT over 1 over p squared. Right. So solving these two partial differentials using the equation of state, we can then write the expression for my dp over dt at constant v, and that is over dt at constant v. That gives me, well, this one times the first term. This is p over nr 1 plus dp. So that's my dt over dv at constant p term, times my negative nRT over p squared equals to -1. Right, just solving the partial differentials one by one. And in here, several terms cancel out. One of my pressure cancel out, nr and nr cancel out, and then you want to move the things to the right. We end up getting dp over dt at constant v. So I move the bottom to the top. Then we got 1 plus bp times p over t. Right, and my minus and minus cancel out. All right. So what's next? Now, in my original equation, what we're trying to solve is du over dv at constant p. And that equals to temperature times this whole thing, 1 plus bp times p over temperature minus p. Temperature and temperature cancel out. We have p minus p, and that ends up with, so p plus bp squared minus p. So my p and p cancel out. We get our final result. That this partial differential gives you bp squared. All right, so if you look back to this problem, it looks like a completely new problem that you never seen in class, but effectively we're using things that we learned in this lecture. First of all, how to translate these partial differentials into measurables, right? So this is the one we went over in class just right now, and also in the thermodynamic relations. And then how to use the equation of state. The equation of state gives us relationship between pressure, temperature, and volume. You can always play around with these differential equations to solve the one we want. And later on, how to basically cancel out terms, solve differential equations. Now, all of these differential equations are not super hard to solve, right? The nature of this differential equation is just like a constant times volume, right? This one is 1 over p, which is p is our variable. So differential equations themselves are not super hard to solve. Just, well, treat these things as constant. Don't get frightened over it. All right, so this is the first part. Now, we can take this one more step. What if we ask you to calculate delta U of this gas going from V1T1 to V2T2? How do you write an expression for delta U of this gas? Right, so the question here is delta U of this gas with the equation of state given from V1 T1 to V2 T2. So it's like one step further. I'm going to keep what we just solved when you are thinking about it. I should have kept the equation of state. So how do we approach this problem? Yes?
So we can do 2 steps. One from V1 to V2 at constant t.
Mm-hmm.
Use that equation.
Right.
Just by moving the dv to the other side of the mirror. Then you have to go from T1 to T2 at constant volume.
Right.
This is just the constant volume capacitor, du dt.
right, so basically what you're saying is let's start by writing out what this one is. We're looking at du as a function of v and t, right? So for any kind of these functions, you can write du over dv at constant t dt plus du over dv dt at constant v. Wait, there should be v. Sorry. Right, so that's writing out the total differential. And do we know what this partial differential is? And yes, we do. We just did our derivation here, right? So this first one, the volume dependence of internal energy at constant temperature equals to Bp squared dV. This one here, du over dt at constant V, that's one of our fundamental equations. That's just our heat capacity. It's our CV dt. Right, so we're looking for delta U. Obviously, we want to take integration on both ends. So we do the integration. We get delta U equals to the integral of Bp squared dV plus the integral of CV dt. And like what we said, we're treating them as state functions. So whenever you have like V1, T1, you can always imagine you go to V2, T1, and then V2, T2, right? So you can solve that integration separately by keeping temperature constant and then volume constant. Nevertheless, coming back here, with the equation of state, we can further write pressure as a function of volume and temperature. So in the first integration, my temperature is constant. My pressure is a function of volume, and you can get that from the equation of state. The second one, I need to give you more information. What is the expression of CV as a function of T? But nevertheless, this one is from T1 to T2 while keeping volume constant. My CV is only a function of T. All right, so what we did is we start from our thermodynamic relations. We use our equation of state, right? We prove that you can solve for the volume dependence of internal energy. And then by writing out what that total differential of my internal energy is, you have these expressions. Taking the integration, you can have two different integrals you'll later on solve for a result. Right? And you can obviously, if this is a multi-step question, can imagine there's a third step. Now I give you the number. Right? What is the volume? What's V1 and what's V2? What's T1 and T2? What is the CV as a function of T? And solve for a numeric answer. Right, so it's like basically what we're using is only the thermodynamic relations and the equation of state. Okay? And that's what I mean when I say my lectures 13, 14, and 15 are all connected to each other. We started simple. We started with these basic equations and calculus. That's all. That's all we start from. And then after these three lectures, we have a way to say calculate the change of my state functions, whether it's delta U, delta H, delta S, delta G, for any material, as long as we know their equation of state. So that's the power of thermodynamics. Okay, I hope I didn't cause any more confusion than I solved. So for this problem, I highly recommend you try what we just did. So right now we did it for internal energy. Can you calculate what's the pressure and temperature dependence for enthalpy? Entropy gives free energy. And express delta H, delta G, and delta S correspondingly. It's going to be the same concept, just try it different ways. Okay, any questions on this part? I'm running very short on time, so I'm gonna skip part B. You'll see my derivation with two different methods for part B, and both of them give us the same result. Part C is pretty straightforward, so we can do that together. So what is our part C? So we have mu jt, right? So remember, mu jt is our Joule-Thomson coefficient. So that's dt over dp at constant enthalpy. And by the way, if in the exam you're like, I forgot what Joule-Thomson experiment coefficient is, and I don't know what the expression is, just ask us. We'll give you that information if you don't have it on your note already. Now in this one, what do we have? We have dt over dp at constant enthalpy. Now we're facing a problem, right? In our thermodynamic relations, we don't have a partial differential that is at constant enthalpy. So how do we approach that problem? Right, typically, whenever we have three variables linked together, remember, we can always use this one to link the three variables together, or to link the partial differential equations together. Or in this question, what we're doing is we're writing dt over dp at constant enthalpy times dp over dh at constant temperature, dt over dh at constant pressure. That gives me -1. Right, so what else do we know? The first term, this one is pretty much just your pressure dependence of enthalpy. Or the reverse way, dH over dP at constant T. Or the other way to put it is we know that dH over dP at constant T equals to negative TV alpha plus V. And this one is just the reverse of that dH over dP at constant T. And do we know what is alpha? So in here, what is alpha? So this one you can solve using our equation of state. Or the other way to put it is after solving it, I'm giving you the answer. So in here, alpha equals 1 over V times dV over dt at constant P. And if you actually solve that differential equation, you get alpha equals 1 over T. And later on, this one, wait, I think something is wrong here. It should be dH over dt over dP at constant H, dP over H. This one should be dH over dt. Okay. And this one is our CP, right? And then you have a way to just move things around and find out things cancel out to give you 0. No, but nevertheless, the take-home message here is where you're facing a partial differential equation that's not in our thermodynamic relations, right? So think about it. Can you link it with things we know using calculus? Yes?
When you say it's going to be the reverse of the, like the negative TV alpha plus V, is it like positive or is it like reverse? Like
right, so this is the calculus we're using. So back here. No, I didn't write it down. So we have dP over dH at constant T, and that equals to 1 over dH over dP at constant T. And this one, we actually need to move everything to the right and have a negative in front, so it's reversed anyway. Nevertheless, I have the detailed walkthrough on the annotated note, so do check it out later. I do want to go over our true and false problems before we end today on chemical potential. Am I being too ambitious in my problem setting? Nevertheless, so here it's a chemical potential, true and false problems. I'm going to write my definition for chemical potential again. So we have mu I alpha, that's for species I in phase alpha. That's defined as the total Gibbs free energy of that phase alpha over partial differential of the number of more of the species I in phase alpha at constant T, P, N alpha, J not equal to I. All right, so first one, chemical potential of mu I is a state function. Now this one is directly related to the nature of my Gibbs free energy and my number of Moore. My Gibbs free energy is a state function, so thus my mu I is also a state function. So this one is true. Mu I is an intensive function, so we went over that in class, right? So Gibbs free energy itself is extensive, but we're dividing the Gibbs free energy over the number of Moore. Thus, my chemical potential is an intensive function. Next up, mu I in a phase must remain constant if Tp and chi I remain constant in the phase. What about this one? This one is not true since mu I describes the change of my total Gibbs free energy versus the number of Moore of my species. Right, so this chi I is the, this one is only the Moore fraction, but it's not necessarily saying like everything else is constant. Next one, the definition of mu I for a one-phase system is that mu I equals to mu Gi over dNi at constant Tp. So this is a very tricky one since this one is false because here, no. Again, it's saying in my definition, that's a total Gibbs energy. That's not the Gibbs energy of a specific species. This one is a very easy to miss question. Oh, did I? Okay, well, that one is fine. That one is true, so. Okay, next one, F. The chemical potential of pure liquid acetone at 300 K and 1 bar equals to Gm of liquid acetone at 300 K and 1 bar. So what does this mean? This is talking about taking it one step further. So this is a general definition. And if we're looking at one phase, we're dropping that alpha everywhere. So that should be mu I equals to mu G over mu Ni T P N J naught equals to I, right? So that's one phase, multiple components. But what if we have one phase, one component? So in the one phase, one component case, now my mu I equals to mu G over dN over at constant T and P. Since we only have one component, my G equals to the sum of all my components. And now that just equal to Gi, right? We only have one component. So for one component, one phase system, the chemical potential equals to the molar Gibbs free energy of that species. So it's like a different layer. We start from multiple phase, multiple components. If we have one phase, multiple components, we're using the blue definition. And then one phase, one component, we have our green definition. And go back to this one, the chemical potential of pure liquid acetone. So pure liquid acetone tells us this is a one phase, one component system. And then the chemical potential equals to the Gm of liquid acetone at 300 K and 1 bar, the same temperature and pressure. All right, so this one is true. And what about this one? The chemical potential of benzene in a solution of benzene and toluene at 300 K and 1 bar must equal to the Gm of pure benzene at 300 K and 1 bar. So now this one is not true, right? We have a one-phase, multiple component system. The total Gibbs free energy doesn't equal to the Gibbs free energy of specific substances in their pure form. So this one is false. Okay. And I have one more practice problem for you to try it on. So this one is problem 4.34. So it's asking the same idea, right? So now you have already solved the partial differential of U over V at constant T of the Van der Waals gas in a previous example, like what we did here. right? So how do you solve for delta U of this volume change of this gas obeying the Van der Waals equation? It's basically doing the same kind of study here with the new equation of state. So that's all from me today. And if you have any other questions or you want to conceptually elucidate something, I'll stay outside to take any questions you have.